Okay, hello everybody. Welcome and thank you for joining Assessing Energy Performance of Insulating Window Shades webinar. I'm your host, Sean Kelly. I'm the US Sales Manager here at Onset. We're excited to have Dr. Mohammad Heidarinejad and Jongki Lee here with us today. Dr. Heidarinejad is an assistant professor in the Department of Civil, Architectural, and Environmental Engineering at the Illinois Institute of Technology in Chicago. He's also the co-director of the Built Environment Research Group at the Institute, where he leads research in areas of building energy and environmental systems. Jongki Lee is a PhD candidate at the Institute's Department of Architectural Engineering. He's also the VP of the ASHRAE IIT branch. Jongki earned his master's degree from Sungsil University in Seoul, South Korea, with a research background that includes M&V, building energy simulation, IAQ, and phase change materials. Jongki's current focus is energy consumption in high-rise buildings. A little bit about this webinar. If you're having any audio issues, please go ahead and check your settings. The webinar will last for approximately 45 minutes. It is being recorded and will be made available to all attendees after. We'll send an email. And during the presentation, please feel free to enter your questions at any time. The question box is over to the right. You'll see a little triangle to open up that box. We may not be able to get to all the questions, as is typically happens. And when that does happen, what we'll do is we'll follow up. Either a HOBO Onset representative will reach out, or it could possibly be Mohammad or Jongki. So with that, I would like to introduce Mohammad Heidarinejad. Go ahead, Mohammad.
Thank you very much, Sean. Good day, everyone. Thank you for attending our presentation. In terms of the scope of this presentation, given the time constraint, the presentation will mainly focus on the instrumentation selection, like what are the challenges we had to select the instruments, what are the approaches we did for the installation, and ultimately opportunities and challenges, because we work with any, field work. Those are the things that could be very beneficial, and we are happy to come back at different time this year or early next year, especially when we have our publications out, to talk about like the whole study. But I think this is a very good opportunity to share the findings in terms of the sensor network we installed for this project. So myself, I've been using Onset products from like very long time ago. So during my grad school, this is a project that we had, and we were investigating ventilation rates in retail stores. As you could see here, like these are the CO2 sensors connected to those old U12, I believe, data loggers. And also we had to measure infiltration, meaning the unexpected air from outdoor to indoor. So we ran the tubings you could see here. These are the differential pressure transducers connected again to HOBO data loggers. This is a study I almost did it mid my PhD around 2011 or so. And then recently, most recently, before joining Illinois Tech in 2016-17, we were looking at ventilation study in college residence halls, and we were monitoring CO2 levels in dormitory rooms. And that was one of the exciting times, because HOBO Onset introduced these Bluetooth-enabled loggers, and it was super helpful for that. So also, we'll talk about it later today. The new system, it's more functionality that we wished at that time, and a lot of those are incorporated in the new platform that you'll see later that we use in our current study. And some references in the bottom if you need to go back and look at some of these studies. So let's do a poll right now. It would be helpful for us to know the audience here, so we can try to emphasize on some of the things. Let's run the poll at the moment, if possible. So please respond to the question. The question is, what is your primary application? So if it's building performance, environmental research and protection, agricultural monitoring, water resource management, or other, that would be helpful if you could select one of these that it's the most applicable to you. Good. We have almost 70% voted so far, 76, 79. Very good. Thank you. I mean, I teach courses and I'm like excited to see a lot of these responses. Good. So let's see the results for the poll. Very good. So almost 91% focus on the building performance, which is most applicable for this study. But of course, a lot of the findings here would be applicable for others. Let's close the poll so we can move on to the next slide. Let's talk about some of the background for this study, and then we'll look at the instrumentation. So this study was focused on installing a novel insulating shades at a high-rise building, Willis Tower. So these insulating shades are product shade systems. So the whole idea for this new way of looking at the shade is, rather than looking at savings on the lighting, which recently the savings are not as significant as before because of the LED fixtures. The idea is, how can you look at and improve the heating and cooling loads in your space, meaning minimizing those for especially older existing buildings when retrofit is cost prohibitive or maybe even sometimes impractical. So the idea is you use the gap between the window and the shade to absorb the heat and adding an extra thermal barrier. And this is very good for cold climates such as Chicago. And that was the whole idea behind this shade and this study, looking at how we could reduce the heating and cooling in especially commercial buildings for this study. The system is low maintenance. It's designed to be motorized, and if they install properly and controlled properly, they could provide energy and cost savings as the results of this study indicated. For this study, the shades were motorized, and the case study is the EQ office at Willis Tower, and we'll provide more insight in the next few slides. In terms of the shades, how they are being controlled, if you look at this schematic from the control team, Amatis, basically they implemented this controller. So if you look at the left-hand side, you could see these are the motorized shades. They communicate data through this data hub. And the data hub sends the information, or basically the other way around, the controller here send the information to the data hub. So these are all within the same platform, but also the team added these extra layers for the controller. So remotely, any control schedules could be either implemented as unscheduled, or it could be implemented as APIs, application programming interfaces. And that's how we implemented some of our scenarios here, especially the complex one. And of course, you could implement that in the existing building automation system, but for this study was a separate one. And also there are some sensors installed to do the occupancies and the switches for the users to rely on. So if I want to show it in the real application, so you could see this is the occupancy sensor. And as you could see, the light is orange, meaning that we are almost in that space there. So otherwise it would be green. And take a look at the ceiling tile here. This is the one that added by the electricians here. And if you look inside of that, all the controllers that I showed in the previous slide are included here. So basically, this is the controller, the 0 to 10. This is the Amatis controller, and the wiring are the communication, the shades. In terms of the shade by itself, these are the shades. And you could see also the cable here. One thing that I didn't include here is we had the low voltage being installed for controlling all the shades. So throughout the space in the plenum, there were low voltage lines, and you could see the cloth for the shade here and even the motors there. So a lot of those components I showed earlier in the schematic, these are how in reality they were installed. The study by itself was 10 months, so we tried to capture both the heating and cooling, almost about 44 weeks. But with the QA, QC, meaning quality control and quality assurance, we started a few months early, and even we collected some data after the project was over because we were excited to see how the sensors and all our platform operate even after the project was over. So if you want to look at it, we almost installed more than 50 different sensors, monitor almost about 190 variables, and we focused on capturing differential pressure to capture the airflow rates. We looked at heat flux, we looked at the air speed, we looked at air temperature, humidity, motion, occupancy, shade position, and a few other variables that these are just an example here. as you'll see later, we looked at different platforms to make this happen, and we believe our experience would be helpful for future colleagues for our colleagues in future to use. In terms of the design of experiment, let's explain a little bit about how these 44 weeks of the data collection happen. So if you're looking at the table here, the project officially started in May 2021 and ended in February 2022. So if you're looking at each of these cells, there are 2 weeks of data collection, except the last 4 ones. Those are like a week data collection because we were able to collect additional data for the winter season. We had 4 different strategies, and these strategies comes on the back end. We didn't include it here, but through energy modeling and optimization, we developed the best schedules for each season based off the time of the day, occupancy, and orientation, and overall like the space usage. On schedule is very similar to what you see in most commercial buildings for the lighting fixtures, meaning like, the shades go up or down at certain time. Also through the day, it could go up and down, but these are all predefined for that 2 week that we ran the model. The dynamic or smart is looking at outdoor condition, indoor condition, occupancy, and so many factors there to make sure that we use the best of the savings possible. But in reality, a lot of times, if you have the smart solution, may not be the best because you might fight with the occupants in terms of their preferences. Baseline was something we enabled for using the old blinds in the building. So like the idea at the end was compare all the shade solutions with the mini blinds, with the like existing system. So we had to bring back all the old blinds into the building. And then ultimately manual motorized means occupant could set the position depending on their preferences. One thing is important for any of these shade strategies, meaning on schedule, dynamic, and manual, occupants were able to override it. And depending on their override, if we were on a schedule or dynamic, after 20 minutes, the room being unoccupied, the shade goes back to the predefined schedule. One of the things we did, we installed both the shades and the mini blinds in parallel, as you could see here in the figure. And the idea was if you're installing and looking at the baseline, the blinds are only in operation, meaning we move the shades all the way up, remove the switches. So meaning occupants cannot change the position. They only have to use these mini blinds. And if we are looking at the blind, or meaning the baseline calculations and scenario, we only, if you are looking at the shades, we only use the shades and move all the way the mini blinds up. So this is how we try to make sure that we enforce these schedules in the space. We installed 39 motorized insulated shades. 29 of them were in parallel with the mini blind. So we selected those spaces that we try to strategically pick the spaces that have different occupancy, different orientations, so to capture the potential heating and cooling savings from this study. The left-hand side shows when we are using the automated shades in the space. So occupants can move this one up and down. The middle one shows when the shades were all the way up and the switches were removed, and occupants had to only use the blinds here. And as you could see, when the shades are in operation, the blinds are all the way up. So these are a few things in terms of how the controls work for this space. One of the things that's important to emphasize, hopefully for future studies, if you're looking at high-rise buildings, if you're installing shades, especially if you're looking at like winter time, it would be very beneficial to ground the system. So that could remove any potential interferences from the static. And if you're looking at these images here, these are all the grounding happened to remove the static from the system. The other thing you may want to think about it, you may want to get the controllers that they're resistant to interferences. So in that way, you could avoid any challenges that could happen, especially if you're looking at a big space and winter time. So let's gradually, transition to the instrumentation. Before that, I want to mention there are 2 main HVAC systems in this space: VAV boxes, variable air volume. As you could see, these are the ceiling diffusers, and a lot of times these are very good in cooling season because of the air diffusion they provide into the space. Also, we have the induction units here. A lot of older existing buildings, a lot of times they have two systems around the perimeter, especially in cold climates like Chicago, Illinois, in USA. You want to bring the warm air from these to interact the window, and in that way you could have a good air movement into the space. So we had to find a way to monitor these two HVAC systems in the space. So looking to the space, this is the space. You could see that these are the VAV boxes, 11 of them. You could see the ductwork with the diffusers here. The other thing are the diffusers, as I mentioned. You could see also how the shades being controlled. Like if you're looking at this space, all these 9 shades are controlled by one controller because they are only in the kitchen and lounge area. But if you're looking at the offices or conference rooms, they have their own controls. Also, the other thing noticeable here, these are the induction units. They go all the way through the south and the west facing. And then ultimately you look at these mini blinds being installed in these spaces. You could see them in most of the spaces, about 29 of the shades are in parallel with the blinds. And the other noticeable area is if you're looking at these zones, these are the perimeter zones that directly get impacted by the shades. And this part is indirectly get impacted by the shade as it's a core zone. So let's run another poll. It would be very important because some of these are the challenges we encounter ourselves. The question is, what are the important features that you would consider in selecting a sensor or logger? Please select as many as applicable. Like, are you interested for the sensors to be only Wi-Fi only, or maybe Wi-Fi with the built-in storage? So meaning you do not have to go to the site. The data could be transmitted through Wi-Fi. Or a lot of times you would like to have the data inside of the logger, even if you're transmitting it. Would accuracy be a factor? Would battery power be a factor? Or if others, I mean, there are a lot of other factors that we didn't include, but those could be very important. Thank you everyone for responding. I see 52% so far. We are almost getting there. Very good, 70%. 72, that's good. I think 72%. We can show the results at the moment. So if you're looking at the results, very good. A lot of time the remote data collection is important, which seems the most important one for the attendees. Then after that is accuracy, 66%, built-in storage, battery powered, and other. Very good, glad to see this. I mean, we encounter a lot of challenges with some of these selections for our sensors, and you'll see it later in the presentation. Let's move on to our instrumentation. So for our instrumentations, we had to monitor the VAV boxes, induction units, looking at the zone level information. And also we were fortunate that this building had a very good building automation system. So we could capture a lot of information from the system, sometimes extra validate our measurements, sometimes something we couldn't do with the instrumentation. So for us, given the large amount of instrumentations we had, we preferred if the data were transmitted through Wi-Fi and remote. Also, we were very interested to make sure that these sensors have built-in storage, because a lot of times if the Wi-Fi is down, you want to make sure the data is stored inside of the logger. So that was another factor. Accuracy and reliability, another one. We want to make sure the sensors were not intrusive to the space, so occupants could not notice it. Multi-measurement capability, like a lot of the sensors we use, they measured more than one variable, like for example, temperature and relative humidity. And then ease of data download was another one. So if you are looking at these, the first step for instrumentation was like, how can we monitor and log the information for these VAV boxes? We had to measure the flow rate coming out of these VAV boxes, and also making sure at least one diffuser per VAV box was monitored for the temperature and humidity coming out of that. I earlier mentioned about my experience using the MX1102 CO2 loggers. At that time, I wish there was a system to collect all the information, because we had to walk on the back of the doors of these dorms and collect the information. Sometimes the connection was lost because of the building, the structure. But Recently, Onset came with these MX gateways, super helpful. I'll show you how we used it. So we installed these gateways throughout the space. And if you see it, we initially had 2 gateways to monitor the entire space. We realized sometimes the signal is weak, especially for these loggers towards the north side here. So we added the 3rd one here. But I would say even with 2, with some optimization, could have covered this space. And they collected data very well. So we are so happy and fortunate we were able to use this feature. Let me pass it to Jongki for a few slides here, and then I'll take it back.
Hello everyone, I'm Jongki. So let me explain a little bit more about the VAV instrumentation. So could you hit once? Next one. Next please. Yeah. So we trying to measure the discharge air temperature, which is we call the supply temperature from the diffuser. So we place the MX1104 and at the end of the diffuser. Then for the QA/QC, we just have one more sensor U12 to double check whether the number is correct or not. And when we put the cover back, then the occupants never notice there is a sensor or not. Next please. So, and we trying to measure the airflow coming from the VAV box. So we need to understand the VAV box first. And could you hit once? Yeah, airflow is coming from AHU system. Then, and in the box, VAV box, they have a damper, and at the end of the VAV box is coming to the zone level. So next slide, please. So this is a schematic of the VAV box, and we need a 2 pitot tube to measure the difference air pressure. So then in this system we can measure difference pressure, but we don't know what the true CFM is. So we need to find a VAV data set. Could you hit once? Yeah. For example, in the building, they have a VAV box from the TADAS. So for example, unit size number 8, they provide K factor as a 904. So as you can see the right upper the equation, if you want to get the CFM, which is equal to K multiplied by root dP. So if we measure difference pressure, then we can get the true CFM using the K factor. Or could you, next one, could you, yeah. Then we can use this kind of graph to get the true CFM.
Okay, thank you, Jongki. So I'll take it from here. One of the things that we had to develop custom-made differential pressure transducer boxes. We use the Onset pressure transducers and the loggers. But one of the things was important for us, we had to make sure we installed these in the places that there were no outlets. These differential pressure transducers, they need the power input of 12 to 24 VDC. But we designed these boxes, so meaning using these D batteries, and the idea was they last for a few months, and they send the data through these loggers, and the logger communicate with the gateway. So if you're looking at it, the box looks like something like this, and you could see these plastic tubings that Jongki was talking about. They are connected to those pitot tubes, but they saved us a lot of time and resources, because those plenums, it's hard to get access to any outlet there. So one of the things is important when you're installing, and we had to make sure, depending on the CFM, you want to adjust this knob here, because if you're looking at the differential pressure transducer here, depending on the position, you could see the dP across the sensor could measure. So if you're putting it at 0, it would be 0.1 inch of water column or 25 Pascal. Depending on the flow rate, we adjusted this. So that was another thing that was important to make sure we do in the study. The other thing we did, we had a lot of those old the old pressure transducers, but also we bought some new pressure transducers. One thing we haven't confirmed, but I believe these, new pressure transducers, they were consuming less power, so the battery for these lasted longer. I mean, this is something in future others could confirm, but are just like, you know, observation was at the first glance, these might be better for long-term installation. This is an example of how we install it, these boxes, the custom-made boxes. So you could see these are connected to the VAV boxes here, like the tubing here goes to one side of the pitot tube, the other one goes to the other tubing. And these boxes were installed on the drop ceiling, so we could measure the differential pressure and ultimately using the equation that Jongki talked about to convert it to the CFM. The other thing we tried to do, because there were low voltage in some spaces for the shade, we tried to also benefit from that. I believe 2 or 3 of these differential pressure transducers, they were just using the low voltage line there. As you could see, they don't have any batteries. The power line are coming out of these. And we connected that with the low voltage line there. So this was something that you do not need to replace the battery. So it was super helpful for our need for some of these VAV boxes, especially when the low voltage was closed. Of course, making sure that these batteries are operating as expected. So we had to do the battery check. We had to also check the airflow rates, comparing them. So we brought a more accurate research grade instrument to monitor basically the flow and the DP from these VAV boxes. Also, we reconfirm it real time with the HOBO apps to make sure these readings are very close to each other. So that was something we had to do in the study to make sure that the flow rates captured are accurate in our study. We are now transitioning to the induction unit. So basically these units that they're exposed either on the south or west side, we had to monitor their flow rate and temperature reading as well. So one of the things which was also new to me, we used these Onset supported anemometers. The idea was, can we measure the flow rate in these induction units? And some of them, you could see that here, we installed these anemometers on the grill. They are connected to power outlet. The challenge was for this one, we didn't battery power them. We relied on the outlet here. And you could see it also again here. These are the anemometer to measure the velocity. Also, we installed external temperature sensor to monitor the temperature as well. A few interesting observations. So that was new to us. So we had 2 different sets of Onset supported anemometers. This is the TCI F350. You could see it here. It's basically this one. This is the MX1105. As you could see, it has more than one channel. This is the external temperature. So it shows how these wirings are connected. So it was a little bit too many wires, but also it works well for our purpose. But also we observed some differences between this instrument and the other instrument, which is this a TCI F300. For this one, you definitely need 2 loggers, at least based on how we were able to work with it. You had to have 2 loggers. Also, it was a little bit more challenging than the other one, but of course, we are happy that we tried both of them because it was a good lessons learned for our future installation. And the documentation was helpful, but also we reached out to the customer support, and also the team was very knowledgeable internally at IIT. So we were able to figure it out, but they were very reliable in terms of providing the velocity values for the space. Also, the other thing we did, we installed these flux sensors. We had Raspberry Pis connected to these Flux Tech pads for the heat flux. They measure both heat flux and temperature. This is the data acquisition for it. And it was something that we installed boxes to measure heat fluxes coming out of these induction units. So super, again, helpful because we were able to collect extra information, sometimes repeating the same thing, sometimes getting additional information needed for the project. And it was custom made. So it was sending the data through our platform that our research colleague, Dr. Ali, created a few years ago. So it sends it to Grafana dashboard, and it was very good because we could observe the data, we could collect the data, we could download the data, and this was another addition for the instrumentation. We also use these heat flux sensors to monitor the heat fluxes coming out of the window, the shade inside and outside. So we were able to capture information coming from the heat transfer through the enclosure as well. We also installed extra, sensors just to collect additional information. The challenge with these ones, they are offline sensors, so occasionally we had to download. So like this is another anemometer to collect information. This is the U12 to collect humidity, relative humidity and temperature into the space. The other thing I want to mention, we have also these occupancy or basically motion sensors. They collect motion, light level, indoor temperature, and relative humidity. This is something that the control team that enabled the controls for these shades they installed, but it was helpful to provide additional information, especially for occupancy and light level, because for some of the dynamic controls, we use the occupancy value to enable that. Let me pass it here to Jongki to look at the measurements. Some results of the measurement, as I mentioned earlier, this presentation is mostly focused on the instrumentation because we want to share with everyone our challenges and opportunities for future that everyone could benefit from. We are happy to come back and show the results in detail later this year or next year. Jongki, please take it from here.
Yeah. Let me share a little bit of a snapshot of our measurement. So could you hit once? So this is the weather, outdoor air temperature data. So in May, the weather is on the transition phase. So and around September 20, we determined that the fall season has been begun, and in the winter we determined this it is starting from the December 27 and ended later February. Next one, please. Yeah, here we have a hypothesis. VAV usually takes a responsibility in the cooling, and induction unit takes a responsibility in heating. So let me check the data first. So this graph show you the supply temperature and zone air temperature. The black one show you the supply temperature. So between this big gap, the VAV trying to supply the cooling energy to the space, and it usually working during the summer season, but the transition side, like a fall season, there's no operation to cool the space. But during the winter, there's a small gap between the supply temperature and zone temperature because they're trying to avoid the overheated space. Next one, please. So let me double check the data based on the dot plots. So as you can see, the right figure, the supply temperature is usually lower than the zone air temperature. The difference is 3.2 Fahrenheit usually. So we determine that the VAV takes a cooling energy part in this office building. Next one, please. Yeah, and we check the flow pattern. So during the summer, it usually turn on 6 a.m. and it turns off at 5 p.m. But the winter phase, VAV trying to supply the airflow to cool the space because they're trying to avoid the overheated space. That's why the winter phase there's a lot of airflow coming from the VAV. In the induction unit, so as I mentioned earlier, the induction unit takes a heating part. So could you hit once? Yeah, during the summer season, there's no operation for the heating or cooling from the induction unit. However, in the winter season, there's a big gap between the supply temperature and the zone temperature. That's why the induction usually takes the responsibility in the heating to the space. So let me double check our data set. So supply compared to supply air temperature versus zone air temperature, the supply air temperature is 8.6 Fahrenheit higher than the zone temperature. So we determined that induction unit has a responsibility in providing the heating energy to the space. So here's the interesting things. We just complete the survey to the space, and it is past the IRB process, the Illinois Tech, and the reinsured they okay, yeah. Let me explain this one first. Okay, the occupant usually have a more interaction with the shades, not a mini blinds, and like as you can see, the motorized shade left pie chart, 80% the occupants wanna control the motorized shade, but for the mini blinds, they just wanna control the 40%, and also the 30% of occupants answered, I've never touched the mini blinds during the operation phase.
Okay, thank you, Jongki. So let me just quickly wrap up with a few things that would be important and we like learned throughout the process. We were so happy with the MX like data loggers, especially like 1104 and 1105. So if you're looking at this is one example. And we believe we installed this sensor sometime in late 2020 or early 2021. And we just collected these 2-3 weeks ago from the building. We collected the information at the minute interval, and you could see that the memory usage was 81% and still like batteries on it. So they could last for years. So it was very promising to see that. And of course, if you go back to the data sheet and compare the data sheet of U12 versus the new MX11.4, the data storage has significantly improved. So that's why I think the data storage, it's not anymore a problem for these. And especially like they send the data through the Wi-Fi, but also they store it in the sensor, which was very helpful for us to make sure that we can do quality control there. Using the HOBO link saved us a lot. I mentioned about the CO2 experience. So if you're looking at this shows we had 3 gateways. We had like, this is the first 20 sensor install. As you could see, some of them were installed in 2020, some of them later. But also like it shows very well how these data are getting collected. We use their dashboards just for checking the data because you can create different dashboards. And like this dashboard showing the velocity for a few instruments, velocity and temperatures. We created dashboards for downloading data, for visualizing the data in the past week. So the platform was very powerful. We use a lot of the features, but I'm sure there are a lot of more that we haven't touched them in detail. One of the things as a wish list, it might be good in future. Sometimes if the gateway is missing, you have to go back and reset the Wi-Fi. I wish there was a way that the Wi-Fi could come back online automatically. But the good thing is that the loggers are storing the data. So as soon as the gateway become available, the data is pushed to the cloud. So we were happy about it. The other thing I think would be helpful, especially like, there are a lot of documentation, but we learned throughout the process. There are 2 apps you could use on the phone for launching and using the loggers, HOBO Mobile and HOBO Connect. We found you really probably need both of them because the HOBO Mobile was able to give you, at least from our understanding, more functionality to export the data with different formats. Like the HOBO data format was so quick to download, but the others took time. But the HOBO Connect was a little bit sluggish for downloading the data, but it was very good for launching the instrument. So we used both of them together. The other thing would be good quality control. So we did some quality controls in the lab. Like these are the 2 anemometers we tested in the lab, and we realized one of them was not working. So a lot of times it's good to double check the instruments before installing it for a long-term study. We also, tested our approach for differential pressure in the lab. We had a VAV box in the building, and we tested in our lab to validate our findings. I see some questions about the energy savings since we do not focus on this in this presentation. This news article just came out, and hopefully in a few months we'll have our journal papers out. We can share it with everyone and come back to present, but this link would be helpful to address some of those energy saving questions. With that, I want to stop here, acknowledge the partners, Parada Solutions LLC colleagues. They were super helpful, and part of the team, Amadeus Controls, EQ office management staff. They were super willing to work with us. So a lot of these experiments, as you do field study, there are challenges, but they were very gracious, and we are very fortunate to work with them. COMET colleagues, also I want to be grateful to the Illinois Tech, my colleague, Professor Brent Stevens, part of the team and the co-PI of the project. A lot of the students and postdoc work on that. And also there's a disclaimer, this is just the view of me and Jongki Lee here. With that, I want to stop here, leave a few minutes for Q&As. And if you have questions, this is my contact. But as I mentioned, I think probably in a few months we'll be coming back to present probably the results more in depth. But this was a great opportunity to summarize a lot of these instrumentations, because a lot of times those are not covered. And the funniest story is we taught a course, and sometimes these presentations was helpful for students to see how the wiring for some of the instruments are connected to each other. So that's why we try to summarize them in this presentation here. Let me stop here, and then Sean, please let us know if there's any questions, happy to answer.
Sure. No, thank you. That was great. And for you, what I'll do, I'll make sure to share the information that you provided as far as the feedback goes for the HOBO Mobile and HOBO Connect and the gateways as well with our product marketing and engineering folks. Now, as far as questions go, it looks like there's a couple along the same lines here that say, how do you log the data from the pressure transducers and the heat flux sensors? And that's from two different folks.
Sure. So for the pressure transducers, if I go back here, the pressure transducers, if you're looking at it, there was a wire that wire goes to, let's find it, to the MX 1105 or 1104, depending on the availability, because also sometimes you may not have all the instruments or loggers, but let's look at it here. So if you're looking at these, this is the pressure transducers. You have two wires. Those wires go to the battery, so you get the power in. But also you have the 0 to 5 volt, I believe, cable. It goes to the logger. And that time, I think the platform was new, so we ended up using the equations in the data sheet for the, I believe it was a linear relationship between pressure and voltage. So we manually used the 0 to 5 to translate the voltage to differential pressure. So that was how the differential pressure was captured. So we got the delta P. And when we had the delta P, we put it into this equation that Jongki talked about. It. You have the delta P from the instruments. You already know the VAV, and from the manufacturer data sheet, you can get this coefficient. And then you calculate the CFM. For the heat fluxes, they were separate data source. So if you're looking at the induction units, you measure also the heat flux coming from the nozzle, you measure it at the grill. So sometimes the information were a little bit overlapping. Sometimes also new information was collected. There is a paper in the bottom of this when we talked about the heat fluxes. That would be good if you want to look at it. Let me get to that one. Here for this, when we showed this paper in the bottom, it would be good. Also, there's a follow-up paper by Dr. Ali that we looked at the radiators and used the heat fluxes. So in summary, it just something might be good to look at those sources, and happy to explain further if needed.
Great. Yeah, and just so everyone knows, with our loggers, you can take in a signal from a third-party sensor. So that's a 4 to 20 milliamp or a 0 to 5, 0 to 10, 0 to 24 volt DC signal. And for the most part, if it's a sensor that we sell, then when you go into that HOBO Connect app, you'll be able to select the appropriate sensor, and it'll preload. Where Mohammad used some of our older, or actually they're the older Veris differential pressure sensors, with a new logger, and you may have to actually enter the scaling values. And again, as long as it's a linear scale, then you should be good. Let's see. When using the shades and the mini blinds were fully raised, was there any way to monitor the mini blinds to make sure someone didn't use them instead of the shades? Kind of tampering with them?
A good question. I mean, not really, but the way we did, we kind of removed the handles. It was difficult for them to use the mini blinds, and also based off the survey, we realized they prefer the shade. So, but we tried to minimize those. Like if there were no way that we could, measure if they're using the mini blinds or not, but we removed all the handles. It was difficult for them to make the adjustment, but it's a very good question.
Okay, at least you made it tough for them.
Yeah, and going back to maybe the questions and the scaling, even like the velocity sensors, you need to scale it. Like also there's like in the app, you could select the instrument, or earlier I showed the previous example of my work, and that differential pressure was not a part of the onset, but the loggers were able to accept those scaling factors.
Perfect. Is there links to helpful formulas and information? So you had shown those links, or actually shown the formulas. Is there a place where folks can go and get those?
Yes, I mean we can. I mean the presentation. If you look at the K factor, I think here you could see some of the equations for this specific VAV box. Or if I go back here, like this link in the bottom was super helpful to show like VAV pressure dependent and independent. But we are trying to wrap up this in a very formalized journal publication, and we'll be happy to share it with the audience in a few months, and also come back and look at all the energy patterns.
Okay, and that's something we'll be able to share as well when that happens. So we'll be happy to send that out to all the attendees as well. And I believe that is all the questions. So if there are no other questions, I'd like to thank Jongki and Mohammad. This is very informational, and we do appreciate you taking the time to do this for us in Onset customers. So thank you guys.
Sure. Thank you very much for this opportunity, and thank you everyone for joining. Actually, you could see our loggers there, so we just collected them from the space. Thank you everyone, and thank you Sean and Onset for this opportunity.
Great. All right, everyone. Have a great day. Thank you.